search ends up being huge, and your statistics aren't right, and your cost formulas are totally imprecise, and finding the best plan. I can give you an algorithm to find the best plan. Run all the different plans and figure out which one is best. Terrific. You know, exhaustive, exhausting, stupid. It's not something that you want to do. Although the idea of checking on yourself after the fact, if you have to have spare cycles and see what really was a good plan, you know, is the kind of thing that some types of learning optimizers or checking over yourself optimizers actually do these days, especially when you have situations where it looks like, you know, something's taking longer than you expected. But basically, cost estimation, black magic, thaumaturgy, I mean, you know, telling fortune by looking, you know, at cheese or the entrails of a goat or something like that, it's not going to be exactly right. You want to look at CPU and I/O, and even in a distributed environment, network costs, and figure out how all this stuff gets together. If you can assume all the data is in memory, then it's mainly going to end up being, you know, CPU costs together with the networking costs, and there's a lot more in memory these days than there used to be. But the plan space is really, really, really huge, even with a 3 or 4-way join, and with 18-way things, it's ridiculous. So you have to have a way of trying to prune the space and focus on what's going on. So there is something that the system optimizer did, it's not done anymore, where you only look at left deep plans. Well, the idea is, I've got a table, I'll access it maybe using an index, and now I'll access another table for each tuple I find in the table I already accessed. I can find the matching things on joint columns in the next table. So now I get A and B. And now I have A and B, and now I can find things where I've got predicates on A and B that allow me to be able to find the matching things in C. I don't have to look at all things in C, but only the matching things that have C based on some kind of index on one or more columns. So I can get tuples as I get them from AB and pipe them into looking at C. And avoiding Cartesian products because those are expensive to calculate. They don't reduce the number of tuples that I'm dealing with. So what is the notion of a plan? I told you, when we went over relational algebra in 180, this has a lot to do with plans. And the idea is that it's like, and I'm lying a little bit, but it's like a tree of relational algebra operators where you indicate not just what you're doing, but we've seen there's more than one way of doing joins. So it's not just a question of I'm doing a join, but I'm doing a hash join, or I'm doing a merge join, or I'm doing an index nested loop join. So, I mean, there are all these choices. What order do I access the tables? What access path do I use to be able to, you know, get each table, you know, etc. So there are lots of different choices that exist. And then basically, as I said, you don't necessarily push, at least you don't push too hard to the next stage in the pipeline. When I get results of AB, I don't want to send too many tuples up to the place where I'm joining with C, because it would be so busy receiving things that it wouldn't be able to do work. But I might not send it a tuple at a time. I might send a bunch of tuples as I get them up, you know, to be processed. So one of the ways of doing it is just to say, the guy who's doing C says, hey, send me another batch. You know, I'm halfway through with the last batch you sent me. Send me another batch so I don't have to wait for you. And you know, it's a lot like that double buffering thing. You don't want to wait and ask, send me something. I mean, you could finish with all the tuples you got and then say, send me something. Or you could say, I'm going to ask for some more stuff when I'm ready to receive it. So I'm halfway through the batch I have. I don't want to wait. I want to have the next set of tuples that I need ready for me when I need them. So I can send a bunch of things up, you know, rather than waiting for the operator to pull. But as long as I don't drown the guy. You know, ever get in a conversation where somebody's telling you too much? You don't want to have a situation where you're told too much when you're not ready for it, and you're busy drowning in all this data that you got to store and have available, and keeps you from actually doing the work. So there's a question about what plans are considered, and how do you estimate their cost, and also how do you estimate size? Why does size matter in this particular situation? Because the cost of doing operations depends on sizes. The cost of taking AB And joining it with C depends on the size of AB. So it's even if you knew the exact sizes of A and B, you might not know the size of A with the predicates associated. You might not know with the size of B with predicates associated. And then you might not know the thing where you not only have the predicates on A and B, but also the join between A and B involved. So ideally, you want to find the best possible plan. The reality used to be that you want to avoid the bad plans. These days, you find good plans. It really is true. So we'll talk about System R, but I'll also throw in some stuff about other things. Same stupid example, sailors and reservations. We're going to be using all the way through, and you know about the notations that we're going to be using to talk about this. Boring, but the repetition makes it easier to remember what's going on. Okay, so to start off with, there's this word query block. You've seen subqueries before. Now sometimes subqueries can be transformed into joins. You have to be careful about that because, you know, when you transform something into a join, where you're going to go ahead and, let's say, suppose you wanted to select all the sailors who have a reservation. You can say, and I've had people in 180 and 182 in the past who said this, let's just do this as a join. Let's just join sailors together with reservations. And that'll give me the sailors that have the reservation. The trouble is that if a sailor has 5 reservations, that'll give me the same sailor 5 times. So a subquery, this is a classical mistake. It was made in a lot of the early days of optimization. Transforming into joins can be a good thing to do. I'm about to ask you why. But you have to be very careful that the semantics are the same. There is part of an optimizer which is called transformation part of the optimizer that sees about finding alternative ways of writing the query and optimizing bunches of these alternative ways. So transforming, you have to throw in a distinct, which could be expensive. I mean, you have to look at whether or not they really are equivalent when you transform. But what is the advantage of transforming A where there exists B into A join B? The advantage is when I take A where there exists B, I got to start with A and then find the B's. If I do A join B, I might be able to start with B instead of A, which might be better. So there are lots of different plans that you can use, and the transformation may sometimes end up helping you. So here, the idea is you've got the inner query and you've got the outer query. Here, if we're not transforming it to a join, there's the outer block and there's the inner block, or the nested inner block, which corresponds to the subquery. And so the idea is if you have a particular form, if you haven't transformed it into a join, the idea is that you can go ahead and optimize the different query blocks separately with the understanding that you are going to need values from the outside to be able to do it. So you can think of, you know, for each of the tuples in the outer block, you're going to call a subroutine the optimized execution plan for the inner block. It's not the only way you can do it. Again, you can sometimes transform things in all sorts of amusing ways. Maybe I will tell you a little bit about something called magic sets, which started off as a very theoretical thing, but per paper I wrote when I was IBM with some friends a long time ago, it actually ends up being a very useful thing to be able to use in query optimization as a transform of how you execute queries. But in the form we're looking at here, you're going to be executing the outer block, getting all the sailors. There might be, you know, some of the predicates on sailors, maybe where rating is less than 7, but here then you're saying where the age is in the maximum age of sailors who have that same rating. So you're only getting the sailors who have the maximum age of people that rating. So, okay. So there is this query rewrite or transformation thing where it tries to change more into joins because that would allow you to execute in different orders. Whereas if you're treating this as I've told you from the beginning, SQL looks like it's declarative mostly, but this looks procedural because for each outer you have to get the inner. But sometimes you can transform it into other ways of executing it. So you're going to see about, for each query block, you're going to see about all the different access methods you have. And you're going to see about all the orders in which you can access tables. But you're going to focus, if you're following the SMAR approach, with left deep join trees, where you go one by one by one. So you have, what order do you access tables? What access path do you use to be able to, access the tables? And when you have joins, what are the methods or other operations? For example, for distinct, you could sort or you could hash to be able to do distinct. There are lots of ways of executing every different one of the operations. How do you execute the operations? So you pick, if you're going for this left deep approach, you pick some relation you start with, and then you pick next, and you pick next, and you pick next. But things potentially end up exploding. Now, in 180 and 182, when I talk about relational algebra, I talk about transformations, and especially when you start looking at group Y, you would be amazed at the set of transformations that's possible, and that seriously get considered when you look at optimization. A huge number of such equivalences. For example, on selection, we talked about this, variations of this in 180. Selection with a conjunction, you can do them one at a time if you want to. You can do them in any different order. So, right, so it's commutative and associative and all the rest of it that exists when you have selection. On projection, what you could do is, you can project on any set of attributes that you want, as long as you project on A1, at the end, as long as the attributes you need on the cascade are always available at each step. I can't say, let's get rid of age, and then say, now I want age at the end after I've gotten rid of age. Sorry, it's nice to be ageless, but if you don't have the age, you can't deal with it. Joins are associative. Joins are commutative in the sense that you get the same set of tuples, although the order in which things show up can end up being different, so it's a little tricky. There's a question: does the join of R with S join T equal the join of T and S together with R? Again, if you ignore the order in which columns appear, the answer is going to be yes. And what if I join with R and T together first? You have to be very careful about what the columns are in terms of doing that. That might be a Cartesian product. So, again, we're not showing it here, but you have to be careful about what the join columns are and anything that gets written there. But believe me, I mean, there are some really interesting papers about how this thing works, particularly in the context of group Y. The sort of transformations potentially will end up amazing. These are just the easy ones. Okay, so again, what about projection and selection? Do projection and selection commute? Maybe, but it depends. Basically, you can't commute, you can't go ahead and change the order of projection and selection. If the projection got rid of things that the selection needs, same thing as with age. You got rid of age, you can't use age. If you have a selection that says we're age greater than 21, and your projection didn't include age in the result, then these are not going to end up commuting with each other. Okay, so other sorts of distribution, selection between the attributes of two arguments of a cross product converts the cross product to a join. All a join is a cross product with a join predicate that's associated with it. There's also something, suppose that I have a selection which only includes attributes of R. If sigma is only on attributes of R, then the identity written there is true. Then I can push the projection, not have it on the join, but push it down into only doing things on R. And in fact, more generally, suppose that I have a selection, and there are three parts of the selection, and where it's a conjunction of three parts. A selection just on R, a selection just on S, and a selection that involves both R and S. I can push the selection on R and apply it to R. I can push the selection on S and apply it to only S. And the stuff involving both R and S, I can only apply after I get both R and S together, and I do the join or the Cartesian product on them. Was there a question there? So I can push things on a table into that table and do it as early as I want to. Typically, try to do it early. Okay, so you can push parts of the projection into both R and S. Okay, and after you do the join, it might be that there are other predicates that the join predicate didn't help you with. There might be a predicate that says something like, and you can call this a join predicate if you want, there might be a predicate that says the product of this attribute of R and that attribute of S is greater than 90. Okay, it's a silly predicate, people do this. If you want to call that a join predicate, I won't hugely argue with you, but it's not something that helps me get from R to S generally. There are all sorts of predicates that I might need to, apply involving R and S, or R is greater than S plus 10 or something like that. Maybe if you want to call that a join predicate, okay, I wouldn't argue, but can be complicated predicates that are involved. So we're going to look at the different plans, and we're going to look at, first of all, plans that involve one relation. Remember, again, same thing in 180. We started looking at how you define the semantics of queries on one table and then the semantics on multiple tables. So we're going to start off with single relation queries. And if it's single relation queries, then you've got the select projects, and you have aggregates, even potentially group bys that can exist on that. And so basically the idea is you're going to consider, for just that one table query, how you can access that one table. So you've got a bunch of different plans that you can use, and even when there aren't any indexes, you always have a way of accessing that one relation because you can scan the whole thing. So you can always get the value for, you can always have a plan even when there are no indexes involved, because you can always do the complete file scan. And then you can pick the one that has the least cost according to your estimate and use that as a basis of executing, okay? So point is that you don't have to do things one by one if you've got a projection. You're getting tuples, and you want to select the tuples that have a given property, and you only care about certain columns. You don't have to get the whole answer on the selection and then project out. As you get the things that satisfy age greater than 21, you can just keep the relevant columns, the relevant attributes. There's no need to have to go ahead and keep lots of attributes together and do it as a separate operation. So when I said it's like relational algebra, but you can be clever about the flow of things, you don't have to keep irrelevant columns around.
Does that also save space and memory as well? Since
yes. Well, memory anyway, because as you get tuples, because you don't have to write it out. You can if you want to, but you don't have to write the things out. So if you're pipelining, you're avoiding having to write things out unnecessarily. You're just sending it up to the next operation inside the pipeline. So you end up having less use of memory. You're touching tuples because we're assuming that it's row-oriented. You get an entire tuple, but you only have to mess with the parts of that tuple that you care about. By the way, if I selected age greater than 21, and I no longer need age later, once I've selected age greater than 21, age is no longer necessary. It's what have you done for me lately? I'm not going to need age. I only selected the things age greater than 21. I don't need age anymore. Okay, so you need to be able to estimate the cost of each operation, which is going to depend on the inputs that go into it. And we've already talked about how you can estimate costs. That was part of lectures that we had before the midterm, so that ends up being nice. And as we've talked about, you also have to represent size, because the size of your result is going to affect the next part of the pipeline. Okay, and we're going to make an unreasonable assumption, because the more reasonable assumptions end up being hard. We will assume that the predicates are independent of each other. What do I mean by that? It could be that for people whose age is over 40, that there's a higher probability that salary is over 100K. Not so much true these days, used to be, but might be true. So, if I'm doing something where I'm asking where age greater than 40 and salary greater than 100K, I have my selectivity of age greater than 40. Maybe that's going to give me half of the people. And maybe for salary greater than 100, that's going to give me 2/5 of the people. So basically, what's the probability that age is greater than 40 and salary is greater than 100K? The naive, stupid, simple, unless you have something better, way of doing it is to say half the people are over 40, 2/5 of the people make more than 100K, so 1/2 times 2/5 equals 1/5 of the people, both have age greater than 40 and salary greater than 100K. I'm going to be assuming independence. There are things that are done now where you get around that independence assumption, but especially in the system of our days, what the heck else were you going to assume? Unless you have things where you keep track of how independent things are and probabilities, it ends up being expensive. So, reminder, how do we use a clustered B tree? You descend if you're scanning everything, you descend to the leftmost leaf, and then you can scan everything going around. And in the case where all the records are in there, and if it's clustered, we'll assume that it's alternative 1, because it's hard to be clustered unless it's alternative 1. Then you just find the records and they're there. Okay, so if you were in alternative 2, and that's really hard to do, then I'll give you an example where it might be sort of clustered. If you have a situation where the records are coming in time order, then you would have a situation where you store the records in time order in a file, and you create your index in time order. And if almost all the records are coming in time order, then both the index and the records will end up being, in the same order, even though you're using alternative 2 rather than alternative 1. Okay, so that would be a case. But if the things are clustered, even if you were in alternative 2, you don't have to touch each data page once. On the other hand, with the unclustered, then in the terrible case, you'd have to go ping, 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 all over the place. We've talked about sorting based on the page ID, which ends up being a good trick to make sure that you only have to touch each page once. But there are 2 disadvantages of doing that. Disadvantage number 1 is that you have to sort the RIDs. That's work, if you accumulate them and sort them. And disadvantage number 2 is that you were getting the tuples in page ID order rather than the order of the search key that corresponds to the index. So that's a disadvantage as well. So basically, if you have an index on a primary key that matches the relation, then we can basically say, depending on, and often again top pages of the index are going to be in memory. But if we assume nothing of the index is in memory, then the cost of being able to access based on the primary key is going to be cost of the index +1 for a B tree to access the data, and the reason it's +1 is it's a primary key, so there's only one record you have to get. Can't be anything except that, and about 1.2 in the case of a hash index. If you end up having a clustered index that matches one or more of the select terms, then going ahead and using that. If you're going to be, so basically, how much would it cost to scan the entire index and get all the data from the index where it's a clustered index? It's going to be touch each index page, leaf page once. And it's going to be touch each table page once, each data page once. So that's going to be page of I plus page of R. But you also have the index on a bunch of columns. You don't have to touch everything. If I'm trying to get everything where the age is between 20 and 40, and I've got a clustered index, then I've got this, select. It's the thing where age is between 20 and 40. I only have to touch the tuples in the index and in the data where it's between 20 and 40. Right? I don't have to touch all the other data. I don't have to touch any other leaf page of the index except for the values where it's between 20 and 40. And suppose that let's suppose again, we'll go back to age greater than 21 and salary greater than 100K. And if I have an index on both age and salary, so I have an index on both age and salary, a clustered index on age and salary, then I only have to touch the things that have the right value for the select. It's a little bit tricky. If I have age equal 21 and salary greater than 100K, then I can take advantage of both predicates. Remember that matching predicates have to deal with, in the case of the B tree, I can take advantage of greater than, but first column is equals works better, so I can have 3 columns where I use equals, and then another column where I have something where I have a range of values. But I end up having not as great a match if the first column has greater than and the second column has equals. So equals greater than works, greater than equals is a problem. Let me say that again because it's confusing. I care about the order of the columns in the index, and equals on the major column and greater on the minor column works well. But greater than and equals, I can still use the index, but I don't get as much benefit because I have to touch more pages of the index that are irrelevant. Only touching things that are relevant is a win. So RF stands for reduction factor. With a, basically with the non-clustered index that ends up matching one or more of the selects, then basically what I'm going to end up doing is I would basically end up having to touch all the tuples of R, multiplied by the reduction factor of the matching selects. Because again, basically I'm going to have to scan through with every one of the tuples to be able to see how things end up produce. Again, I can play games with the sorting versus having to go ahead and see what ends up being involved in doing it. In the case of the sequential scan, I can just scan every page of R and see what's going on. I'm not going to end up reducing the thing. I'm just going to touch every page when I end up going through it. And again, when there's projection, unless it says select distinct, you're not going to end up doing something where you eliminate duplicates. Only when there's a select distinct do you eliminate duplicates. Two reasons for doing that. One reason is that duplicate eliminations work. The other reason for not getting rid of duplicates is it changes the semantics when there are duplicates. So let's take an example question.
Sorry, on the last one,
yep.
The non-clustered?
Yep.
Why aren't we calculating the overhead of the index as well?
In the case that you end up having something where you end up taking, let me actually figure out about the answer to that question. That's a good question. Frankly, I think that you're asking a good question, which I will answer next time. Okay, so let's see about, so I think there may be a typo on that slide, and I'll fix it. Okay, so here we have a very, very simple query. We're selecting sailors where the rating is 8. Again, I think this partially ends up doing part of the fix. This one is right and the other one is wrong. In the case where you have an index on the rating, then if we assume that there are 10 ratings and we assume everything is uniform, and we'll get away from that uniformity assumption later when we talk about histograms. But for now, we'll assume that each of the 10 different ratings from 1 to 10 has 1/10 of the tuples. So basically then there are going to be 1/10 of the 40,000 tuples are going to be returned. So you're going to get 4,000 tuples inside your answer. So that's a number of things that you get. In the case where you have a clustered index, then the reduction factor is going to be 1/10. You're going to have to touch all the pages in the index and all the pages in the relation if there were no predicate. But because there's a predicate that says we're only touching 1/10 of the tuples, we're only touching the tuples where rating is 8. And because it's a clustered index, we're only going to be touching 1/10 of the index pages, leaf index pages, all right? And we're only going to be touching 1/10 of the tuples. So it's 1/10 of pages of I plus pages of R. So that one's pretty straightforward. So let us go ahead, and this is again, I think the typo that's on the other page. This is correct and that thing isn't. And so in the case of the situation in which there's an unclustered index, again, we're going to have things where we end up doing the following. We're going to be touching, again, 1/10 of the pages in the index. And again, you see why, exactly the same reason. This is a question of the midterm, why it's going to be 1/10 of the pages of the index. And then what you're going to be doing is for each of the tuples that's in the answer, you're going to be doing a disk IO. So again, that's the fix that I need to do on the other slide. For what you're going to be touching 1/10 of the pages that you have inside the index. Again, exactly as it was for the clustered index. But now for each of those 1/10, you're going to be doing a disk IO for each one of the tuples in the answer. How many tuples are there in the answer? Tuples of R divided by 10, right? So 1/10 of the index pages, and for each tuple in the answer, you're going to do a disk IO. How many tuples are there in the answer? Tuples of R divided by 10, okay? Number of keys, 1 is 10, so it's going to be 1/10 of the pages plus 1/10 of the tuples. So that's, again, the fix that should be on the other page, okay? Where I throw in the pages and tuples on that. So it's going to be 1/10 of the 50 pages in the index get touched, and for each of the tuples that's in the answer, unless I'm doing that clever sort thing, I'm going to be doing a page X to be able to get what's involved if things aren't sitting inside. So it's 1/10 of 50 plus 40,000. This is the correct one, what was on the other slide as well. Question on this? Let me just go over that one time, and then actually I'm going to have to end pretty quick because I have to go to my other midterm. But basically, 1/10 of the index pages are going to be touched to be able to get the ratings. The ratings where rating is 8. And for each one of the tuples in the answer, I'm going to have to do a disk IO in this naive assumption. How many pages are there? Tuples of I divided by 10. Tuples of I divided by the number of keys that we have inside the index. So that's what the result turns into. And if there is no index on SID, then you're going to have to retrieve all the tuples I'm sorry, if you have an index on SID, so seller ID is another column that you have. If you have an index not on rating, but you have an index on SID, you can use the index. You can also do a relation scan. What happens if we go ahead and use the index? Again, the index doesn't help me reduce things at all. But I could go ahead and use the index. And so the cost of using the index is going to be, basically 50 plus 500. 50 for the index pages and 500 for the data pages. Okay. And if I use an index, an unclustered index, it's going to be 50 plus 40,000. Again, same thing over there where there is no reduction factor involved. But I may be better off just scanning the table rather than going ahead and doing that. So if there are 500 pages in the table, 500 is going to be less than 50 plus 500. So I can use the clustered index, but it's not going to help. It's not going to help. So the third alternative is to just go ahead and do a complete file scan of the 500 pages that I have in the file. So number one, I will give back the midterm with a fix to the question that I got.